Hello, in this video we will be seeing how to find the sum of left leaf nodes in a binary tree and also compute the space complexity and time complexity of the solution that we will be building in JavaScript. Before jumping into the solution aspect, let's first understand the problem statement. We will be given a binary tree that will look something like this. So you will have a root node and left children and right children, and we have to pick the left leaf nodes. What is a leaf node? A leaf node is a node that will be not having any left or right children. For example, I go on the left side of this specific root node, which is 7. Now 7 doesn't have any left child or a right child. So this is a left leaf node. So we have to find a sum of all these left leaf nodes. And we will be building a solution using a depth first search traversal approach, wherein we will be doing a pre-order traversal, wherein we will first check the root, then we will go on the left side, and then we will go on the right side. That will look something like this. I will start with my node. If my node is going to be null, I will just return 0 because then I'm not going to have any sum. I will go on the left side of this specific node. I will say for the left node that I have, check if it is not null. So if I have a left node and the left node is going to be a left leaf node, and to do a check for left leaf node, I will just say, does it have any left children or right children? If it doesn't have any left and right children, then it's a left leaf node. So if the criteria is fulfilling, wherein it, for this case it does, because this is a left node which is a leaf node. So I will just pick it up and then I will move on to the right side of my tree that I have received and traverse the left subtree first, then move on to the right subtree now. So I will go on this side, I will again say go on the left side, and then we will go on the right side. So I will, for this specific root, I will say, hey, what is there on the left side? Is a left node existing? Yes, it exists. But is it a leaf node? It is not a leaf node because this has a left child. So I cannot consider this for the sum aspect. I will then make sure that I traverse the left subtree for this one, and I will go all the way down here, and then here I will say, is this a left leaf node? Yes, it is. So I will pick it up. Similarly, now that I have visited all the left subtree, then I will move on to the right subtree. So for the right subtree, I will say go on the right side. Then for this right node, see if you have a left node. Yes, it has a left node. Is the left node a leaf node? Yes, it is. So then consider it, which gives me 16. And this is the first search because we first go on the left side, visit everything on the left side, then we go on the right side. For the right side also visit everything on the left, and then move on to the unvisited right side, which can also have a left side associated with it. So we are traversing in this specific manner in a depth first search fashion. And that's pretty much in terms of the approach towards the solution. And let's now convert whatever we covered into code, and the code will look something like this. So we will have a function sum of left leaves. It will receive a root node, and first thing we check is whether it's going to be null. So if there is no root node itself, we will just return 0 because that's the outcome here, because we need to return the sum of all the left leaf nodes. If there is no root itself, the sum will be just 0. Then we will check whether the left node exists and if that left node is a leaf node or not, because first we said go here from the 4 value node, go on the left side, is the value existing? Yes, it is. And then check for the leaf condition. So I will say root dot left is not null, and this node on the left side has to be a leaf node. And to check the leaf criteria, we say check the left child and the right child. If none exist, then it's a leaf node. So root dot left has to be null, and root dot left dot right also has to be null. Then I can safely say that this is a leaf node. So I have leaf node. So I have met my criteria for my left leaf node, and with this I can then just return whatever value I picked up here. So I need to consider 7 now, so which will be root dot left dot value plus. Now I will go on the right side and visit the right subtree because I'm doing a pre-order traversal. So in that will just look a recursive call that looks something like root dot right. Just make the visit on the right side now to do a traversal. Otherwise, so I picked this value, then I went on the right side. Value I had was having a left child. So 21 had a left child of 13, but this was not a leaf node because this had a children of its own. So in that case, I just do a recursive call to find the left leaflet on this specific node, which just looks like making a call to the function that we have received and do root dot left. So I will go on the left side now and try to find whether this is a leaf node or not, having on the left side. And similarly, then I will visit the right side. So first I will go on the left side, which will be covered by sum of leaf here, and then I will also make another call wherein I will try to traverse on the right side now. So root dot right, and that's pretty much it in terms of implementation. I will go here, pick the 7, I will go here on this side. I will go in my else condition now because the first criteria is not satisfied as this has a leaf node on the left side. So this check that we have put saying root dot left is not going to be null. So then it will go in this else condition. It will make a call with this as the root. It will see the left node having 4, this being the leaf node. It will just add 4 to it. Then we will move on to the right subtree using this function, and it will go here and it will say this node has a left node, yes, and that is a leaf node. It will pick 5. So it will do 7 plus 4 plus 5, and in the end it will going to return 16. And in terms of the time complexity that is going to be involved here, it's going to be big O of n, because as we said, we are going to make these recursive calls for achieving depth first search, and in worst case you can have n nodes and you can just keep visiting them via this recursive call stack. So because of that, the time complexity is big O of n, and in terms of the space complexity, that is also going to be big O of n, because in worst case if you have n nodes and you visit all those n nodes, then you are going to place data into this call stack every time you make a recursive call, because we have a recursive call here, we have a recursive call here and here for all the 3 use cases we mentioned, and that will be consuming the space within the call stack in JavaScript. And that's pretty much it. Thank you for watching. Please like and subscribe.